I'm going to show you today is a handball demo using the virtual world technology to implement in this particular handball. What you see on the back over there, on the computer monitor, TV monitor, there is a simulated box. Within the box, there is a ball sitting on the floor. The box has 4 sides but no top. There's a bottom floor, and the ball can be grabbed by means of my hand and interact with it by hitting it, throw it, and so forth. The particular I/O device I'm using for interacting with the ball is a data glove, as shown over here. On the back, I have optical sensors, as well as a 6D position sensor for image device. Okay, now I can, using this particular device in the virtual world and mimic my gestures. For instance, I have here 5 gestures. This particular one is the open hand. I'm using the open hand to hit the ball, as you will see a little bit later. This is a slight bending of the fingers, and this is a little bit more bending of the fingers, and this is a fist gesture. I'm using the fist gesture to grab the ball, as we will show later. This is the pointer gesture. Now, there's only 2 of the gestures being used, the others not being used, and we probably can use it for something else. Now I'm going to grab the ball. I have to move. You can see here, in this virtual world, it's difficult to see where you are in the 3D position. So I'm using a projective marker indicating where my hand position is on the floor, which is rectangle tool. So as I move towards the ball, we're getting closer, and grab the ball. Now notice, when you grab the ball changes the color, which is also a visual cue, very useful to tell you grab the ball. Now let me move the ball to a certain height and then let it go. You see the ball bouncing around. When the ball hit the floor, it's making some noises, which helps you to know ball actually impact on the ground or the sidewalk. Now I can throw the ball horizontally, it's bouncing around the wall and the floor. Here we're simulating some simple physics with the gravity and the natural bouncing. I can throw the ball upward and try to grab it. It takes a little bit of practice to do this right. Although this is a relatively simple demo, nevertheless, it demonstrates all the principles used in a virtual world and all the technology associated with it.
You're about to see a virtual laboratory for exploring a particular fluid dynamics problem, that of 2 interacting vortex tubes. The tubes you see below are the data, visualized as isovalue surfaces of constant vorticity. We can explore them with spoken commands, hand gestures and movements, and virtual devices like the sliders you see at the right. The laboratory can respond with motion, music and other sounds, and simple speech. I'll begin by saying the start command, and you'll hear the computer acknowledge OK. Start.
OK.
First, I'll fly around the data by aiming a flying gesture side to side and up and down. I can fly in and out. If I find myself in the dark, I can ask for a light. Spotlight.
OK.
If I get lost, I can return home with a reset gesture. I can grab the tubes to rotate them. I can change the experimental conditions by pointing at and grabbing the sliders. Changing the color occurs continuously as I move my hand. But it's more instructive to step the simulation forward in time to see the tubes interact. In this case, the recalculation takes several seconds, so we're playing thinking music to show that something is happening. This relatively simple virtual world is composed of 12 processes on 7 computers, coordinated by a central dialogue manager. Finally, I can quit.
Are you sure?
The Naval Postgraduate School's NPSnet system is a real-time 3D visual simulation system written in the C programming language with calls made to the Silicon Graphics GL library. NPSnet takes advantage of model databases, real-time graphics techniques, and graphics tools developed at the Naval Postgraduate School. The goal of the system is to simulate ground or air travel over terrain for any vehicle described to the system. Terrain databases can be any of a variety of standards, including SIMNet SDIS and Defense Mapping Agency digital terrain elevation data and interim terrain data. Realism in NPSnet is enhanced by means of textured terrain and objects and environmental effects such as fog. The system is networked and designed for multiple vehicle interactions through multiple workstations connected by way of Ethernet. The system serves as a virtual world exploration tool and serves as the visualization front end of a mobility expert system developed on a networked Lisp machine. The purpose of the mobility expert system is to explore algorithms and proposals for autonomous vehicle and interactive vehicle interactions. NPSnet is a flexible system. Its collection of model databases is extensive. Vehicle descriptions can be changed and replaced by way of menu selection, and engagements of any sort can be rapidly depicted. The system contains an internal script generation and playback system, which you see in play here through the movement of over 50 vehicles.
One of the advantages of simulation systems is we can explore and interact in worlds that do not exist. Dun, 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 dun. Here we are at the assault landing of the 1st Amphibious Cow Brigade. Notice that we have the helo cows flying air support for us. Also, we have the ground attack cows moving out in a smart military manner. These are not your average barnyard commandos.
Let's cut to the hills.
We are currently flying a helo cow, observing the formation of the attack cows below us. Notice the smart military manner that the cows maintain their distance from each other. Splat! Whenever you notice, cows are stronger than the trees and progress right through them. Splat!
As in all virtual reality systems, our moving vehicles can go right through three-dimensional objects such as trees, buildings, and other cows.
Boy, that was a close call. It was a moving experience. Questions that we had to answer with this simulation system is what happened when a cow dies. As we shall see momentarily, when a cow dies, it turns into a hamburger. So we are currently using the helo cows, firing missiles, as good all attack cows, into the attack cow formations.
Cows can go easily through hamburgers. Check that on the right.
Naturally, as we attack the helo cows, they drop to the ground and form little patties. Stop! We are now driving one of the attack cows as it rampages through the stampede. And as we see when we come up over this ridge, the cows are stampeding through Zydaville. Under the power lines, carnage, the carnage. You deserve a break today at Zydaville.
Well, as we roll up to the last patty, we wish you a bon appetit. We can't afford to have real music on this tape because we have so many sponsors. We'll see you all later. Bye-bye.
Accelerator board. What? He's not going to meet with an accelerator board. And how are you doing for field? No, it's the copper. Copper is loading and copper registers. $1,000 ones has a lot. The $200,000 to $300,000 ones has a lot less lag time and higher frame rate. The objects. When it comes to having fun, your system works pretty well.
That's cheap.
Should I shut the room lights so you can get the monitor better?
Okay. Yeah.
We can do this in color. We can run this. This version.
I've been working from NASA up for over 3 years now.
I didn't save a version of real-time digital filtering place sounds in 3 space. So coupled with Doppler shifting and the graphics, you can find the object just by listening.
When that's coupled with the boom, you can literally turn your head to find the sound. That one's not optimized for the boom right now. This is for shutter glasses, right, John? Or is it anaglyph? Okay.
Shutter. Show you the shutter stuff too later. Dogfighting it. A little bit simpler model than this. It was running at 30 frames a second constantly. Here you can see it's running about 20 to 30 frames a second. This version was custom just to do dogfighting. The current software I'm working on is totally generalized to do anything you want.
And are you doing...
Where did you get your sound for the guns?
So I created it.
Welcome to the world of vision, an artificial world, a virtual reality. Vision is a networkable virtual environment terminal offering real-time human interaction with a database generated and maintained by computer. Database objects have many attributes, such as sound, color, the ability to move, gravity, and so on. When calibrated, Vision can recognize user-defined gestures which can be used to control the Vision system. Vision provides a totally new interface between the computer user and an application. The database is viewed in 3 dimensions using stereo goggles and is directly manipulated using normal body gestures, such as point. The VPL iPhone consists of a pair of color LCD display units giving a 3-dimensional image. A magnetic sensor on top monitors the position and orientation of the head. In this way, Vision can render the database from the current viewpoint. The VPL Data Glove employs fiber optics on the back of the fingers to measure finger flex angles. A second magnetic sensor mounted on the glove monitors hand position. Vision will closely mimic the movements of the operator, making it possible to interact with images in an intuitive way. The pick gesture is used to pick up the teapot here, and the drop gesture can be used to throw it. A simple gravity attribute has been attached to the teapot. Let's try that one again, but this time we'll add a sound attribute. User-defined menus allow Vision to be easily connected to existing applications and modeling systems. Many applications, from numerical analysis to molecular modeling, are directly concerned with 3-dimensional objects and their relationships in a 3-dimensional space. The correct visualization of these objects and the comprehension of their geometrical properties is often essential to the success of the application. The molecule is made up of simple objects, benzene rings in this case. Objects can be split by simply pulling them apart. Alternatively, the whole molecule can be moved as one unit. The spider's head has been assigned a function to automate it. It will track the position of your hand. Let's explore some acoustic possibilities and then fly through a village like Superman. Each of the objects in the drum room has been assigned a different sound attribute. The operator's hand is displayed as a drumstick. To play the drums, simply hit them.
Hi there. I'm on my way, I'm making it. I've got to make it show, yeah.
This low-cost image generator shades sorted polygons at more than 30 frames per second, even without taking advantage of the hardware screen clear feature. The models consist of polygon meshes which are compiled into the correct format before runtime. Any object can be compiled in this way. This flight simulator offers 25 frames per second image generation. Any number of image channels can be connected, allowing wraparound viewing without loss of performance. The high-performance front end runs the simulation model and allows multi-user networks of simulators to be constructed. The textured image generator renders images in non-real time in software. Here is a flight simulator using the textured image renderer. All the polygons are edge anti-aliased. Fully anti-aliased texturing with mipping is applied to all polygons to avoid texture aliasing at distance. The system can also accommodate transparency and fog or distance fading.
rocket?
Yeah. Going after it. Yeah, so if we now look at these views. This is the view from...
This poor little camera's having a tough time focusing. That's good stuff.
There it is, see the explosions. I guess it's still tracking.
Did the bomb hit that, or did we hit it?
No, the missile did. It's another train. Yeah, what else you want to do with this one?
I think we've got that one.
Okay, so let's stop camera.
Great.
Let's pop in the train.
It's pretty good in black and white. Did a good job on that one, John. That's nice. rocks, did you say to that?
Yeah, that's right. It's pretty boring right here. Rocks or something. Okay, that's it for this one.
Okay.
Well, tell me when you're ready.
I'm rolling.
Oh, you're rolling.
Just started, yeah. I got it. The shots are nice too. Track that well.
In 1986, Very Vivid and the Vivid Effects Group created the world's first live interactive video system. This allowed you to step in front of the video camera and actually have your image be brought into animated television environments. As you moved around in front of that video camera, so did your image inside of those animation environments. You could see yourself as you reached up to animation around you and actually interact with that animation, causing various effects, both in sight and in sound.
Since 1987, Vivid Effects has been using this technology and applying it to the worlds of art, education, entertainment, and corporate communication.
These are a few examples of some of those applications.
Computer graphics world now.
reality here. Now. 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 Losing reality now. Reality now. We're magic. Reality here. We're losing reality now. Losing magic. Reality now.
Hi, I'm Bob McDonald, and I'm curious about everything. Like why things are the way they are, and why they're not something else. Like, what kinds of realities are there, and how did I get into this different one? I wonder what's behind this door. You know, every time I open a door that I've never opened before, I kind of feel like Alice, I guess Bob in Wonderland, because you never know what's on the other side.
Even Alice would have found this world hard to believe. This is a world that exists only in a computer. Computer people call this artificial reality virtual reality. For years, we've been putting words and numbers into computers. Now we can put ourselves into a computer. On our side of the computer screen, interacting with a virtual reality looks like this. Pretty silly, huh? Believe it or not, all this flailing about is actually me controlling a computer. See? What's happening is that my image has been transported into an animated environment. It's my digitized image that's playing the drums, not me.
Animation around me all has triggers in it. When I reach out and touch them, we get sounds and we get visual effects.
Vincent John Vincent, a creator of virtual realities, explains.
Virtual realities are realities that exist really only in the minds of computers, that you're able to view and actually step right into. You're able to actually move around inside those graphic video environments and experience interactive control over the animation and graphics around you.
Entering a virtual reality is as easy as finger painting and a lot less messy. There's no keyboard, mouse, or joystick. As a matter of fact, I don't have to touch anything but air. All I have to do is stand between an ordinary video camera and a dark background. The camera acts as the computer's eye. It identifies me against the dark background because my clothes contrast with it and because I move. The camera captures my image and sends it through a network of software and hardware to the computer monitor. We combined what the camera sees and what the computer sees by splitting the screen.
Tinkerbell leaves.
Notice the mirror image.
Zips out.
The real me controls the action of the digitized me inside the computer world. When I move my arm, my image moves its arm. Vincent and I can dance to the music and make the music dance to us. What am I doing now? Why, goaltending, of course. Although at the moment they're mostly used to make music and art, Vincent hopes for a bright and varied future for virtual realities.
Well, it's an art form on certain levels. The other aspects of it that make it more scientific are some of the virtual natures of the animation. So you can do, challenges and tests. People can, simulate basketball, skiing, that kind of effect. Can use it for training, definitely on that level. Physiotherapy, where people are getting feedback of their physical movement, and it's both visual and auditory. It's fun, which is the other thing. So there's a lot of scientific directions that you can take the technology in as well, but always on a level. It's fun, whether it's science or whether it's art.
I ask this of everybody who's doing something really neat. What makes you wonderstruck about this?
I'm not sure. There's quite a few different things. One is just the fact that we've been used to looking at ourselves in the mirror for so long and then watching television, and now it's kind of a combination of both of those. We can watch ourselves in television, step in there and become part of the world, and it's like a looking glass. You're stepping into another world, and that sense of reality when you can actually touch things and pick them up that aren't really there. It's kind of it's magic that kind of captures people's imagination.
Stick around, we'll be back.
New Music takes a look into the future uses of computers in music next.
In the Mandela system to me?
Okay, it's a new interactive video device, which means that the performer can stand on stage, have his image brought into a computer through a standard video camera. The computer then mixes that with graphics that an artist has drawn up, and as the performer moves, he actually triggers events that are associated with those graphics.
Most important uses of Mandela system technology is the development of interactive virtual world adventure games. Because of their interactive nature, these games challenge the user both mentally and physically, as well as allowing for creative expression. Vivid Effects has placed custom-designed virtual world installations in many cities throughout the world. Located in museums, galleries, exhibitions, malls, theme parks, and other public spaces, Mandela installations have generated an overwhelming response. It's the custom installations. Vivid Effects is now creating Mandela system modules for commercial locations. The user enters these 10 by 10 booths in order to participate in one of many possible experiences. One possibility is a sports game, such as this one, called You Be the Goalie, created for the NHL's Hockey Hall of Fame. There are other sports, such as soccer, and similar modules involving baseball, basketball, and skiing are currently being developed. The Mandela system is highly versatile. It's been used in production for film, television, and video, as well as a teleconferencing tool with Bell Canada for interactive transatlantic communication. It's also been adapted to a variety of business applications. Interactive graphics for corporate presentations. Trade show presentations and installations.
B.F. Goodrich's origins, I was a proud leader of the rubber and tire industries. However, innovative breakthroughs in polyvinyl chlorides would lead them in the direction of becoming world leaders in the vinyl plastics industry. Other applications include computer, business machine, and television housing.
We choose to see it.
Sales motivation videos.
Never before have the opportunities for all of us been so tremendous. If only we choose to take advantage of
them. Of course, as originally conceived by inventors Frank McDougall and Vincent John Vincent,
the SIGGRAPH Assembly Modeler is an example of the integration of virtual reality technologies such as stereo vision, direct manipulation, real-time interaction, and physically based modeling into a commercial CAD environment. The Assembly Modeler was developed at the request of Northrop Aircraft under contract from the Air Force Material Lab for Northrop's automated airframe assembly program. Within the assembly modeler, users can import data, such as the F-18 speed brake assembly, shown here on screen, from the in-house CAD system, NCAD, and analyze part and tool assembly procedures and simulate part and tool kinematics in relation to other subassemblies. You are looking at the flying mouse. Based on human factors requirements, the assembly modeler needed an intuitive and non-encumbering 3D input device. After user evaluations performed with the VPL Data Glove, it was concluded that a new device was required. Existing in-house research into new devices was accelerated with the development of the flying mouse, a device which smoothly combines 2D position sensing with 3D position and orientation sensing. Lifting the flying mouse causes it to transition from the familiar 2D position sensing device into a 3D position and orientation sensing device. Notice the direct mapping between the motion of the user's hand and the cursor motion on the screen. The 2D arrow paradigm has also been extended to 3 dimensions with a 3D conical tipped arrow. The arrowhead is composed of 2 parts, the 3D conical arrowhead and 2 concentric circles which are not occulted by scene elements, thus allowing the user to always find his picking volume. The differing scales of scene elements in an assembly modeling session dictates the need for altering input device gain for operations on objects of different scales. The actions and motions required for the assembly of aircraft instrumentation is distinctly different from a wing body joining operation. We have been researching the use of tactile feedback in the flying mouse, which is shown here. The left button has been retrofitted with a 3x3 matrix of elements used to generate the tactile cues. To create a convincing and productive desktop virtual reality application, effective output or cue generation is required. For the visual cue generation, the StereoGraphics crystallized hardware was interfaced, giving the user additional 3D cues to help guide the user through this portal into a virtual shop floor. User observations verify the increased ease in assembly selection and maneuvering in and around the assembly as presented using the stereographics display. The ability to quickly toggle between full screen viewing and menus on screen allows the user to get maximum viewing space and visual cues. In addition, automatic visibility toggling of active menus, dialogues, and windows also gives the user unobstructed viewing during simulated operations. Real-time user interaction and system performance was a requirement in implementing this system. This is achieved by swapping lower complexity model copies or levels of detail, as shown in this demonstration. To better support the simulation of assembly operations, the assembly modeler provides snapping of parts to their final assembled position as dictated by the NCAD database. Here, a hydraulic cylinder is being positioned into its clevis. A final position guide box highlights when the part is close to its final assembled position. Parts, their assembled positions, and their kinematic relationships are loaded directly into the assembly modeler from NCAD. Levels of detail are automatically generated for use by the assembly modeler's performance manager to maintain update rate. Of primary importance is to allow the user to attach to parts and reposition them in relation to the assembly. When a part is attached to or grabbed, relative moves of the input device simultaneously move the part according to the 6D device scaling set. Rate moves of parts are also possible while a part is grabbed. Also important is allowing the user intuitive control of the viewer position. We use what is called the world in hand metaphor. This metaphor allows the user to manipulate the world view directly. The apparent motion of the world maps directly to the motion of the 6D input device. In this scene, 2 work cells containing IBM pick-and-place robots are depicted. Here, the assembly modeler is used to inspect the assembly line, from the component placement station to the wave soldering station. Parts may be constrained in any of the 6 degrees of freedom, with the option of having totally free or totally constrained parts. Note the joystick is able to move only in roll, pitch, and yaw. The slide switches are only able to move in translation, and the range of translation is limited to the physical range of the slide switch. The assembly modeler database also allows groups of sub-assemblies to be assigned specific kinematic solutions, as shown by this flight simulator motion-based assembly. The 3 rotational and 3 translational flying mouse input channels have been assigned to the movement of the motion-based cab. An inverse kinematic solution determines the resulting motions. Rotational and translational motion may be constrained according to the specific design requirements.
This is a postcard of the downtown market plaza for the town of Karlsruhe, Germany. Do you see anything odd about this photograph? Check out the tracks. Here's about the same point of view, but from the tracks. I was commissioned to movie map the town from the tram point of view for an arts festival this coming May in Karlsruhe. The project's a lot like the MIT Aspen movie map, but with tracks. The software isn't done yet, so I'm just walking you through some of the features of the project. One thing nice about the tracks is that when you have options, it's clearly visible. So the software will stop at an intersection. You'll choose by hitting one of 3 foot switches, left, center, or right. It will take you through the turn. And then you'll continue. You'll be able to control your speed by using a broomstick-like lever to give you continuous control. Unlike the Aspen project, where we shot at 1 frame every 10 feet, here I shot at 3 different intervals. Through the pedestrian area, I shot at 1 frame every 2 meters. And for most of the rest of the town, 1 frame every 4 meters, right here. I haven't normalized the speed, so we're literally going twice as fast now. And for the outer parts and rural areas here, 1 frame every 8 meters. Let's look at it again, but a tad faster. 1 frame every 2 meters. Four meters, and 1 frame every 8 meters, but you'll have much more tight link control of the speed. Here's the rig I used, a tram car. I tapped the odometer, an electronically triggered stop frame film camera. There'll be a simple graphics map and cursor second screen showing where you are. And here's just a little example of going from the town of Karlsruhe to the village of Durlach and back. And again, I'm just sort of playing with the speed here, but without the luxury of having a continuous lever yet. So right under the hill there, here, is the village of Durlach. Slow down a bit. Stop at the bus stop. And head back out to Karlsruhe. And here's just a little teaser out in the more rural area by the Black Forest. My interest in doing this, by the way, is not so much to simulate reality as much as it is to abstract it. Once you start being able to go at speeds that you can't do in the real world, you start seeing things that you couldn't otherwise see. Also, the VR world is presently dominated by computer-generated imagery with hardly a clue how to digitize the richness of the real world. Surrogate travel like this will offer eventually a template for such integration of the two.
Very good. This way, Mr. Swallow.
This is a reenactment of what you as a guest would experience.
Right this way. Okay. Here's your chair. Have a seat. Here's the menu. Everything's listed on here. Your waiter will be right with you.
Good evening. I'm Gluto. I'll be your waiter this evening. Are you ready to order? What will you have? One moment, I'll be right back with your order.
Your tuna sandwich.
Recent discoveries indicate that our true outer space begins beyond the orbit of Pluto.
The Milky Way galaxy. Farther, we are seeing
Your pollock beans.
And how did you enjoy your vegetable? Good. And now for your dessert.
Your cherry pie?
Thanks for dining with us. I hope you come again. Bye now.
Here's the table the students built. It really is trapezoidal. Hole in it for rear screen video projection. The plate was frosted glass. Kodak LCD video projector. A mirror under the table for it. A hidden switch for the waiter to call up the next menu item. A Mac in the other room. Cheap way to get micro switch out, tap the keyboard. And quick and dirty HyperCard stacks for the wait people only.
This recording is only for use of the SIGGRAPH VR Gallery Review Committee. Copyright 1991, IBM Corporation. Modern computational power offers an unprecedented capability to model the real world. The computer can become a virtual laboratory, permitting the rapid and convenient exploration of hypothetical environments. It can provide multisensory channels for interaction, sight, sound, and direct manipulation. Rubber Rocks is an instance of our virtual reality laboratory. It combines highly interactive 3D graphics, hand gesture and speech recognition, three-dimensional position sensing, sound effects, and speech synthesis. Rubber Rocks simulates a room, a hand, and the physical behavior of flexible objects with widely different properties. You can create, delete, and change the objects and the properties all by voice commands. There is a selection of 10 object shapes, including all the regular polyhedra and some other interesting solids. The size, mass, hardness, and breakability of an object are all independently settable. Objects can also be colored 7 different ways. You can push, hit, and grab the objects in the room by moving your hand. You can also manipulate several objects at once. When the objects bounce around the room, against the walls, and against each other, they deform and may sometimes break. The wide variety of objects and their interactions offers a very rich and interesting virtual world. All contributors are members of the Computer Science Department at IBM T.J. Watson Research Center, Hawthorne, New York, except Greg Turk, who is at the University of North Carolina at Chapel Hill. This tape was written and performed by David Ravenhorst. So our system not only recognizes the three-dimensional position of the hand, but it also recognizes several different postures. Fist, point, and flat. And notice there's a drop shadow on the floor underneath the hand to help determine where the hand is in the 3 space of the room. Drop shadows are also present on the objects. Cube.
Cube. Whoops.
Cube.
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 What?
What? There is a cube and another cube.
Erase.
Erase. The room is clear.
Green.
Green. There are no objects to recolor, but the next one will be green.
Cube.
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 Cube. Whoops.
What?
What? There is a cube and another cube.
Erase.
Erase. The room is clear.
Red.
Red. There are no objects to recolor, but the next one will be red.
Cube.
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 What?
What? There is a cube and another cube.
Help.
Help. Try hitting or catching the cube or the other cube. Whoops.
What?
What? There is a cube.
Tetrahedron.
Tetrahedron.
Red.
Red.
Sheet.
Sheet.
Cube.
Cube. Hold your hand still.
Cube.
Cube.
What?
What? There is a tetrahedron and a sheet and a cube.
Help.
Help. Try hitting or catching the tetrahedron or the sheet or the cube. Whoops.
What?
What? There is a tetrahedron and a sheet.
Erase.
Erase. The room is clear.
Cube.
Cube.
Cube. Cube.
Cube.
Our system runs on a small network of IBM Systems 6000 computers to run the 3 major parts of our system: a physical simulator, a renderer, and a dialogue manager. We also have a VPL data glove, a Behemoth 3-space tracker, an IBM Music feature card for sound effects, a speech synthesizer, and a speech recognizer.
The system architecture is designed to support multiple simultaneous users in a virtual world. We plan to bring a multi-person system to SIGGRAPH. In addition, the system supports device remappability, where we can easily replace input and output devices. For example, if speech input were not available, we could easily replace it with the glove and tracker. The user could point to this selection on the display. The contact person for the SIGGRAPH Virtual Reality Gallery is Larry Koved, K-O-V-E-D, at IBM.com on the network. 914-784-7935.